Okay, so today is just, well, I should say this video is just a theory video on quantum gradients. So because most of these implementations are in Penny Lane, um, that will go in the Penny Lane playlist, but I wanted to make this sort of independent of code because I'll also be doing stuff with this in TensorFlow Quantum. So I wanted the basics to exist independent of any programming language. And so um, basically we are just going to look at how exactly these gradients are done for parametrized quantum circuits. We've already used most of these. The parameter shift rule, for example, is an example of taking a quantum gradient, but that's just built into TensorFlow Quantum or Penny Lane without, we haven't we haven't discussed that at all. We just say, differentiator equals TFQ dot differentiators dot parameter shift without really explaining it. And so I figured it would be good to go over some gradient information. And so we know that for some parametrized quantum circuit, we have this function. We can set it, we can see that it's equal to this, I shouldn't say 0. It's equal to the expectation value of our measurement operator here. And so this might be something like why am I writing that out? Pauli Z operator, for example, is a common one. And then this is our parametrized circuit, the variational quantum circuit. And it's just, if you're familiar with quantum mechanics, you know that the expectation value of an operator, as we've discussed before, can be written as this, and so this is just, these are the initial wave functions. So that might be equal to just the starting state, for example. And so this is the expectation value of our measurement operator. And so this could be, maybe we're doing classification, and this is the expected output of the circuit. So how do we do that's the question we want to answer. How do we take the gradient of this circuit? And so there's a lot of normal approaches. You can do, finite difference, central difference, etc. You add a little bit and subtract a little bit and take the difference. So there's a finite difference which looks something like f, or I should do theta, h minus f of theta all over h, and that's not h bar. And this is the finite difference method, but it's an approximation that has associated error, and this error increases the more relative to what h we pick, and also the size of the circuit. So it's not the greatest answer, and so we can do actually exact, or analytic, I should say, gradient. So we call the finite difference numerical because it's you're using, actually I shouldn't say this is why it's called numerical, this is why I call it numerical. I mean, it is called numerical gradient, but I don't know if this is the etymology of the numerical part, but because you're just inputting numbers and getting an approximation, whereas the analytic is calculated from knowledge of the system. For example, finite difference can be used in neural networks, but the analytic gradient, or the backpropagated gradient, is because we know that we have knowledge of the forward paths and of the operations being done. And so we can do the same thing for gradients for parametrized quantum circuits, because we know one key thing, and that's that if we have our, let's break it down. So we had, we have our BQC. We can break that down into individual circuits. So, it could be U1 theta, U2 theta, etc. So we can break that down as far as we need. We can write the expectation value of U2, U1, and U1, U2. We can do that. And so I'm just going to break it down and assume a single operation just for simplicity, because you can break down the entire circuit into single operations. So we know the single operation can be decomposed. Obviously, simple operations like Rx and Ry. So we know like Rx of theta, for example, is equal to, just getting it up so I don't lie to you, is equal to cosine of theta over 2 times the identity matrix minus I sine theta over 2 times poly x. And so that's just the definition of what the Rx operator is. And so with this knowledge, we can break down any of these rotation operators into basically something of the form, a plus b cosine plus sine, plus c sine. We can write this. And you can write theta over 2 without loss of generality, because you can, this might, if we're writing this for Rx, you would just do, 2 times theta here. And so that theta over 2 doesn't really matter. But if we know that any circuit can be written, or any this operator for rotations can be written like this, then we can see real quickly that, hey, this is a lot easier to differentiate than we thought, because we know the derivative of cosine. We can write it, for example, analytically. This is a definition of cosine. So if we do the derivative of cosine, we can see that it is equal to cosine of x plus s plus, minus cosine of x minus s all over 2 sine s. And so we can do the same thing for sine. This is exactly the same. If we're taking a derivative of sine of x, this is just replace these values with it. And so the reason is because we know there's, if you look up the trigonometric identities, there's certain rules about, cosine and sine, that you can add things to it. That, if you've ever taken, trigonometry classes, you'll know that. And it's also important to note that the derivative of cosine of x is usually just written as negative sine of x, and derivative of sine of x is just cosine of x. And so you might be asking, wait, why are we writing them in such a complex form when everyone knows, everyone who took Calc 1 knows these derivatives? And that's because we're going to be utilizing these terms to get the gradient. And you'll see that in a second. So if we know those terms, then we can say, okay, if we do the derivative of u, which probably wasn't the best idea because this isn't, u has a lot of meanings with respect to theta, we can see that the a term from here disappears because the derivative of a constant is just 0. And so we get the form of u of theta plus s minus u of theta minus s over 2 sine of s. And so this is the derivative, the parameter shift rule. So for example, if we choose s equals pi over 2, this becomes 1. So it just becomes u of theta plus pi over 2 minus u of theta minus pi over 2 all over 2. But you can choose s to be any value, and this will work. And so this isn't usually the form. Well, I guess it depends what background you have, but this isn't always the form that you'll see it in. But this is the form, so I'll link these papers down below. This is the form as presented in the paper Estimating the Gradient and Higher Order Derivatives on Quantum Hardware. So this is where the this format comes from. But you'll see another format pretty frequently, which is from the this is also the format that TensorFlow Quantum uses. This is from Gradients of Parametrized Quantum Circuits using a parameter shift rule and gate decomposition by Gavin Crooks. And you will see this format pretty common. I think I've even used this before, where this time the derivative of the circuit is equal to R F theta plus pi over 4R minus F of theta minus pi over 4R. And so the reason this looks different but is actually the same is because it's just derived differently. Because we can also write the parametrized gates as e to the negative I theta g, where g is the generator. So we can decompose this into, maybe 3 times poly x plus 2 times poly y. So we can decompose this into some poly operators. And so g is just these generating set. We can write this out, and if we do a lot of math, I'll link it in the paper. I'll link the paper. I'm not going to do the math here. We can get this formula. And the reason is that this R here, R equals the eigenvalues of this G. So if we're doing the poly operators, the eigenvalues. Oh, sorry, I shouldn't say this is the eigenvalue. This is related to the. Yeah, that was a mistake. It's not the eigenvalues. That's I was thinking of a different implementation in my head. But that R value depends on the parametrized gates. So for the poly gates, R equals 1/2. And we can see this works out to be the same in that it becomes pi over 2 over 2, which is the exact same as here. And so basically, this formula is equivalent to that format. And so you can see it really wasn't that hard to derive. We just have to know that these poly gates or these parametrized gates can be expressed in trigonometric or exponential coefficients. And so then we can see easily that if we can do the first derivative via this technique, we can also do the second derivative. So we just have, I'm going to use the first terminology. So if we want, maybe we want the second derivative, where this is I, J, we can see we just have to apply, should do f of theta. We just have to apply this terminology twice. So we have this whole, I'm going to try and fit it in here. Let's see if I can. F of theta plus S times, this is just the index basically. I should actually reverse those. So this is I plus theta J. And so then we have minus F of theta plus S of negative I plus theta J minus, okay, well you can see the pattern here. There's 4 cases where this is positive, positive, negative, positive, positive, negative, and negative, negative. And so that's just the terminology, and then it's all over 2 sine of S squared. And so this is, you can see this is pretty easy to derive. You have the first, you just apply this twice and this formula right here, and you'll get that result. And so from here, if we can calculate the second derivative, it's pretty easy to see how we can generate the Hessian matrix, which would be, which is, theta 1, theta 1, to derivative of theta 1, theta n, to theta n, theta n, and this is theta n, theta 1. So this is the Hessian matrix. And this is used, for example, in Newton's optimizer. If we have normally gradient descent is theta plus times a gradient f theta, but this time Newton's optimizer is plus n times the inverse Hessian times the gradient of f. And so this can be very useful here. And so the last thing I wanted to discuss is the Fubini-Study metric, which is sort of analogous to quantum Fisher information. And so that Fisher information tells us, like, for a given parameter, how much does that sort of influence the expectation value. And so this is really more about the circuit rather than the parameters, but it can also be used in updating them. And so we can see that this is defined, and I'll link the paper in the quantum natural gradient paper, because as you know, in classical natural gradient, you take the inverse of the Fisher information matrix and then multiply by the gradient, and you update using that instead of just the gradient. And so we can do the same thing with the Fubini-Study metric. So if we have I, comma j, we can see that this is the negative of the theta I, theta j times the parameter prime, parameter there. So we have that, and we can see that if we replace this, we can see this is the probability that basically the survival probability of the state is 0. I should write probability. And so we can see that we can measure this on a real quantum system by the probability of attaining the all 0 bit string after applying the unitary operators or the parametrized quantum circuit. And this is, of course, in the Z computational basis. And so if we use the parameter shift rule and basically plug this in here to get the unitary changes. So because we know that the theta prime is equal to these, we have these unitary changes, that we are doing to the circuit. Or I should do, yeah. And so we can see that we're applying these changes to it, although really, this should be probably reversed. And so we can see that using this parameter shift rule, because we know this is a function of parameters that are being updated, so theta prime is the new parameters, we can write this out. And I'm not actually going to write this whole equation out. I'm going to steal it from the paper because it is a lot to write. But we can see this is actually equation 16. Oh, I realize you cannot see that. This is equation 16 in the paper. You can see that you can see the parameter shift rule, but in this case s equals pi over 2 in action, where we're breaking it down into the 4 terms, just like we did to calculate the second derivative, because remember, we can see that this is a second derivative calculation, and so we're breaking it down into 4 terms, and then we are applying this parameter shift rule, and we can get this Fubini-Study metric from this rule. And so that's pretty much, let me just hide that. And so that's pretty much it. We saw how we can calculate first order gradients in addition to second order gradients. I'll link all the papers that I took this information from, and they include information for higher order gradients as well, but I didn't really cover that because that doesn't seem as useful. And then I'll go over, these were all basically the quantum gradients 100, 200, and 500 in the Q-Hack challenge. And so I'll go over how to do them in PennyLane. I have a little bit of starter code in TFQ that I'll hopefully finish up as well. And so, but this is just a theory video that's independent of any programming language. And so, yep, that's it.